So I actually have now added additional functionalities is I actually run all the strategy and run the roadmaps for the software and hardware for Radeon Open Compute, which includes the historical FirePro server products. So we're actually driving a brand new branding and strategy, and we're putting software first. And this is really what I'm going to talk about today. I actually led an initiative that we call the Boltzmann initiative that we launched at Supercomputing 2015. And today we're actually launching the ROC platform, which essentially is the new branding for what we're driving underneath that initiative. So for our group, we're the Radeon Open Compute group, and there's a reason that we're driving this direction. Thank you. Is we believe that it's time for the GPU infrastructure to actually get opened up, right? So we're starting to look at what do we need to do to meet your needs. So see if this will go forward. So one of the things I got lucky in the last year is I started working on some very interesting infrastructure that we were bringing out to the DOE and a number of customers like that. So we got to talk to them quite a bit. And we listened to you about what you really needed for software infrastructure. It wasn't taking the historical FirePro card and the Catalyst driver out and trying to get that stuff to work. We really had to start from the get-go with a new foundation to meet the needs of HPC and ultrascale. The other thing is we had to refocus our commitment to you as customers. So we're listening to you adamantly about where we're trying to go and how to build solutions. And then critical to this was we had to change our philosophy of how we're driving our platform out. And so we want to drive an open foundation. What I mean by this is we're building a driver infrastructure that's open source from the metal up. All our compilers, all our drivers, all our runtimes will be actually being delivered into the market through GitHub, and as also in binary form. And we're calling this the ROC platform, which is the Radeon Open Compute platform. So what is it? It's actually, we're giving you a new stage to play on. And so one of the things that's been critical was we had to go look and address one of the core abilities, which is giving you a foundation that's a 64-bit Linux kernel driver that's headless, right? Which essentially historically was challenging for some of us in the past. The other thing we did is we took 4 years of history and brought it forward. We actually were doing this thing called HPC technology. It's the reason why I went to AMD 4 years ago. I was brought in to stand that organization up. And we've actually done a lot of research on what does it mean to do things like coherency, signaling, getting the GPU to be a first-class citizen in the whole stack. We decided we want to take this technology and extend it across not just the APUs, but bring the DGPU into it, and then look at how to bring other partners that we work with, like Intel, and merge our GPUs together to get maximum efficiency out of it. And the other thing is we wanted to focus on overall latency, and that was one of the key things that we looked at HSA, which is looking at queuing times, pulling the latency out of getting that job onto the device so it feels like a first-class citizen. And then the other thing is we wanted to make sure you had a solution that was optimized for the node. So that means having multiple GPUs in a single node, and then scaling across the rack and having, so you can have a GPU A talk to GPU B from server A to server B efficiently. And then the other thing is we wanted to build a foundation that allowed academics and researchers to explore what's possible in GPUs. I've looked at a lot of research over the years, and my favorite one was someone was building a file system with a binary blob. It's just, that's a lot of work, and essentially you really need something that's more open where you can actually twist and turn the driver to best match your needs. So what we did? So one is we put a serious investment. So last June, we started this project. It was the Boltzmann initiative, and it really focused in on the core foundation that you're looking for. So one, we put peer-to-peer multi-GPU support into the stack default. We built a standardized loader in code object format because one of the things we wanted to do that's different than historically saw on GPUs is we're taking the compiler out of the runtime and driver. So we're giving you the ability to have a static offline compiler to generate your code. We're going further. We're actually generating native ISA. So we publish our GC and ISA manuals so you can see the best attributes of our compiler at the assembly level. we went further than that. We realized that you also sometimes have hot loops, and you want to be able to go in and tune those hot loops. So we're adding in GC and ISA, assembler and disassembler to allow you to really dive into your code. And then, as everyone's interested right now, is they're interested in Docker. So we've been working on this for a while. I've been tracking this market for a while, did some consulting with other markets. Like the last user, I used to be in the visual effects business. I ran Digital Main's render farm. And it's very critical for us to drive large scale out. I could tell you horror stories about rainstorms and all kinds of crazy stuff when I was at Venice Beach. Trying to run an infrastructure for 1,200 artists, right? So, and we've added user mode DMA, which actually I'll show you why that's a benefit to you. And the next one, which is one thing that we want to do, as I said earlier, which is take latency out of the system. The purple lines that you see up there are system to device and device to system. That was our catalyst driver, which is basically showing the efficiency of a sweep of basically data set sizes versus gigabytes per second of transfer performance. What we did is we actually attacked the latency. That's why the curve shifted. So now you get relative efficiency at about 64K, but what you historically got at about a 1 meg transfer. This is very important when you're attacking problems like DNN, because you deal with these really skinny matrices and you got to move the data quickly. So we're really attacking that. And then on top of that, you add user mode queues, and it drops even more latency out of the stack. This is how you get closer and closer. So you have the benefits of something like a CPU. We didn't stop there, because one of the things that became clear, I've been working on tools for a long time, from SGI to MIPS to Intel to Motorola, Metroworks. And one of the things that I learned a long time ago, you have to make it really simple. I started my life as a material scientist. And one of the things as a material scientist, you want to be able to approach and solve your problem, right? So one of the things we looked at was we wanted to build a new kind of compiler that's single source. So it generates C++ code that actually generates the CPU and GPU code from a single source environment. So it allows you to quickly and simply solve your problems. The other thing is we realized underneath the stack, you've got to support the basic capabilities to get the maximum acceleration out of it. So essentially, we have async kernels, we have the ability to do scratch pad memories, and then we're also extending it to support the native capabilities of C++ 17, 14, parallel STL. We're also adding OpenMP into it. So you can think of this as going to be, what we see is the next generation of how you drive heterogeneous computing. And we're working with a number of projects out there to actually harden this compiler. The other thing is, we realized we had to give you choice. And one of the things that we did unique, before, when you came to our shop, I feel like it wasn't a John Belushi skit. You actually remember the Billy Goat, where some of you came up to me, you said, I want an egg salad sandwich. I said, you know egg salad sandwich. Give me a cheeseburger. You want a Coke? I'm giving you a Pepsi. You want chips? No chips, right? So we decided to actually go after the end market in a different way. So one of the things we realized essentially is we heard loud and clear that you wanted more than just OpenCL. So we are actually adding the C++ compiler. We're adding actually now a solution we call HIP. So when you're driving down the road, when you drive a CUDA, you want to have ROC on it, right? So we're going to make you all HIP by actually having ROC. And so what we're doing is we're HIPifying the CUDA code and actually have a new porting strategy for bringing your code across, and we HIPify our code. And historically, for a CUDA programmer, what's great essentially is that you typically see something like CU malloc. Now the operation looks like HIP malloc. It's very simple for them to understand. It feels like CUDA, but it's in a new platform. And the other thing that was unique about what we did is we now allow you to actually operate CUDA, the HIP code, on top of a CUDA device using MVCC or using the HCC, so on our device. So you have portability now. You had a new way of getting portability of your code. So you start in HIP, and then you can have portability against both architectures. Whoops. The next thing is we've been working closely in Austin. I'm from Austin now, moved there about 16 years ago, and I'm working with Travis Olivan's company, Continuum Analytics. They love our platform because now they have an open platform that they can get access to the low-level driver and drive maximum efficiency out of their Anaconda Numba platform. So we're actually bringing Python and Python acceleration so you guys can bring SciPy, Numba, pandas and other scikit style applications through acceleration on the GPU. We've seen great acceleration on the APUs, and now we're seeing great acceleration on the DGPUs as well. So we work very closely with these guys. It's a fantastic foundation, and then we work closely with them to extend it so you get even more better attributes at it for doing acceleration. And how we see our strategy is historically is this example that I told you before. We're changing the way we're looking at the market because we see that we have to expand the base of developers. For GPU computing to move to the next level, it truly has to move to the next direction, which is starting with the historical hardcore C programming models and CUDA-style programming models, and we have to evolve. And so one of the things we're doing is essentially we give you the ability to do HIP. Then we extend it again further through the single source programming model, which essentially is much broader and much easier for you to get access to. I got to accelerate because I got 3 minutes. The other thing is, we're not stopping at the foundation. It's critical for us to focus in on the key application areas. So biomedical, machine learning, oil and gas, bio-IT, astronomy, finance, molecular dynamics, right? And other areas as well. And so our teams are actually starting to invest, and I've actually been investing for the last year on basic applications in space to really tune this stack up. And so we're delivering the usual suspects. You got to have BLAST, you have to have FFT, you have to have sparse, you have to have a random number generator that are accelerated against the GPU and in this environment. But we go further than that, right? Which essentially you have to go after the third-party library. So we're working with Cocos, which is a fantastic library to run because it's really intensive on a compiler stack. We work with Charm++, we're with HPX, and then we have a litany of DOE apps, mini apps that we've been asked to actually tune against the stacks, historical stuff like Xbench and HBMG and MiniMR and CoMD. So I work closely with my AMD research team, and we bring all these through, and we're making them over. And then the other thing is we're adding in capabilities for neural networks. So we're actually adding an open source convolution, which we call MLOpen. We've actually been working closely with Torch 7 and Caffe, so we have ported all this infrastructure up on top of the stack, and we're bringing OpenVX over as an open source stack as well. The areas where it's kind of interesting is we're working with Chime. Chime essentially is a unique radio telescope to everybody else. It probably looks like a half pipe. So it says 1 minute on the shot clock. So what are we doing to actually use this? We're actually using the Radeon Open Compute platform. So we actually use the Fiji Nano, which is probably the best undiscovered GPU on the planet. It's 175 watts of peak power. It's 46 gigaflops per watt. It does 8 teraflops performance, and it's 500 gigabytes per second memory bandwidth. Fantastic device, and then we build it in 2 with the S2. And why is it important is when you look at single precision numbers, it's critical to have almost a square curve, right? This is basically a roofline diagram. So we're looking at performance in flops versus flops per byte, right? So what we're seeing is it's giving very effective flops per byte, so 18 seconds. And we're getting, one thing is you can't drive 425, which is essentially gigaflops per byte. What I want to show you is that we're also driving effective characterization on memory bandwidth, so you know that we can see 430. We've seen 440 as of last night. And then the other thing is we've been working with CGG on a number of seismic data. This part, the S9300, is starting to show about 3.8x the performance of our competitor right now on their codes. This is typically RTM, full wave inversion. And we're working with Supermicro and Mellanox to build stacks. That's a 1 petaflop stack that's under 400 grand, right? So, and sitting under 30 kilowatts of power, which was important to me when I was doing stuff. So, and then this is what we do to test. This is what we call Rock Monster. This is basically 4 levels of PLXs, and it stresses any stack out. It's got 32 ASICs inside the system to really push the system as far as you possibly can. I want you to know we have a hardened stack. Looking for it, yep. But that's it.